Hello, thanks for joining me for this series on vectors and scalars. I'm Anna Mackay. Let's have a look at an opening problem. What is a vector? How might we use it? So in this example, if you imagine an aeroplane flying in calm conditions at 800 kilometers per hour due east, and then a cold wind suddenly blows from the southwest at 31 kilometers per hour, pushing the aeroplane slightly off course. How could you illustrate that, the movement and the wind, using a diagram that's to scale? What operation do you need to perform to find the effect of the wind on the aeroplane? And could you use a scale diagram to determine the resulting speed and direction of the aeroplane? So in this topic of vectors, that's the sorts of things that we'll be looking at, so the skills behind being able to solve that problem. And vectors have lots of applications, particularly in physics. As you can see at the bottom here, where we've got other examples: acceleration, displacement, force and momentum. This is just a bit of background stuff here. So in that opening problem, the effect of the wind is determined by both the speed and the direction, because you can imagine if the wind was coming from different angles, the effect that it would have on the plane would vary. And so the quantities, which only have magnitude, are called scalars. If it has magnitude and direction, then that's a vector. So think about the magnitude of the wind would be 30 kilometers an hour, and the direction was if it was east or west or north or south. And so then that's a vector. Right? So a scalar is, or has magnitude only, so that's a number, like that 30 kilometers an hour. And a vector has magnitude and direction. So that was that wind, say the 30 kilometers an hour from the east. You have to use arrows to represent that. And the length of the arrow, so when it's drawn to scale, that gives you the magnitude. So it's always important to have a ruler for this topic. So velocity and speed is a what? So I've probably jumped ahead there, but speed is a scalar because that's just the number, but velocity is a vector because that would tell you the direction. Getting used to some of this terminology here of the magnitude and scalar. And sometimes when we abbreviate the word direction, you can see that little N there, like written in the power. That's one way, so we don't have to write the whole word. All right, so an example here. The velocity of a car is 40 kilometers an hour in a northeasterly direction. So just while we're on here, the 40 kilometers an hour, what is that? That's your scalar that tells you the magnitude of the vector because it's now got a direction. So how do we draw a scale diagram? Hope you've got a ruler. Thinking about where that goes. Northeasterly direction, so that is exactly on the 45-degree angle in the northeasterly direction. So using your ruler, I don't have one. I'll just try and be as neat as I can. We have north there, east here. So northeast is on that 45-degree angle. But how far? We want to draw this to scale. So a classic thing we often have is 1 centimetre is 10 of the units that you're after. So we've got N here for our newtons. I don't have a physics background, but so bear with me if I ever make little tiny errors. The 3 equals that we use here, do you know what that means? It means equivalent to. So we're not saying 1 centimetre is equal to 10, it's newtons, it's equivalent to. And how do we draw that? So if we have 40 kilometres per hour that we need here, and for each 10 of them we have 1 centimetre, then we need 4 centimetres. So 1, 2, 3, 4. You'll be using your ruler and label what you've got there. Okay. Other examples of vectors include displacement and force. Oh, and acceleration. And particularly if you stay in with a maths methods type of course and you come into Year 12 math methods and we do calculus, when we look at applied calculus, motion diagram, well, just motion with displacement, velocity and acceleration and looking at the speed, that's an applied context. So we need these skills that we're developing here in vectors for some of this stuff. Just a bit on the notation. Okay, so a vector from the origin O to point A is called the position vector of point A. And look at the way it's written. We have capital O and A with an arrow on the top. Sometimes in textbooks you'll see that written in bold. However, if you are handwriting a vector, you don't need to sit there and colour it in darker to make it bold. The way that we do that by students, or when a teacher writes it on the board, or in this video, is with an arrow on the top. But just be prepared to see it in a textbook as bold and to know that it's the same thing. To define the magnitude or the length of a vector, we write it in this way. Now, you may or may not have come across these straight brackets before, meaning modulus. So that's the positive of whatever number's in there. Or again, it could be written around the bold or the small arrow, that sort of thing. Okay. We say that for A to B is the vector which originates at A and terminates at B. Just some of the terminology there, the start and the end points if you like. And the AB is the position vector of B relative to A, because B is where you end. Equality here. So this is really important. Two vectors are equal if they have the same magnitude and direction. So having a look at this vector A here, it's actually the same if you shift it, so it has a translation of some sort, sideways, up, down. However, the things that have to remain the same for equality are how long it is, its magnitude, has to be the exact same length wherever that is, and the direction. So they have to be the same. So essentially, if you could take one of those A's, which way around is it for you, and move it and superimpose it onto one of the other positions, then you've got the same vector of A. It doesn't necessarily matter where it starts. So that's going to come in handy for one of our examples. Negative vectors. If you get asked, okay, so let's say we've got the vector A to B here, but if you asked how do you get from B to A, so going in the other direction, that's the negative of that vector. And so as you can see here how that's written. So it's written negative A and it's the same length and in the opposite direction. Okay, an example here. So PQRS is a parallelogram in which P to Q is A and Q to R is B. And we want to find vector expressions. So for the first one there, for QP, let's have a think about that. So how do you get from Q to P? Well, we know that if we went from P to Q, it'd be the vector A, but we want that same distance, same length, but in the opposite direction. So our answer for that one is negative A. Negative A. Next one. Colours all mixed up here, but that's okay. RQ. So there's our arrow on the top, capital letters there. RQ. So you find R and you find Q. Okay, there's a vector that runs along that way, B, but it's in the opposite direction of what you want. So to go from R to Q, it's the same length as Q to R, but in the opposite direction of the vector you've been given. So we've got negative B. Next one, S to R with your arrow. S to R. S to R. So you want to start at S and end at R. Is there any way you might be thinking, okay, could I go all the way around the parallelogram? Yes, one option. Or look at this vector here, P to Q. It has the vector of A. And when we talked in vector equality, if you've got the vector A and you can move it, so a translation in any direction, up or down, but keep it the exact same length, you could shift that over, that vector A, over so it's superimposed on the line SR, and therefore that would be equivalent. So your answer to get from S to R is A. And notice it is positive A as well because it's going in that same direction. And then the last one here, what have we got? S to P, S to P, so that's going across there. Is there another vector that could be superimposed, if you like, that could be equal? And that would be, well, something to do with B, but it's not B, it would be what? It would be negative B. So just finishing that off there. Okay, so that's a quick introduction to vectors, and next we have geometric operations with vectors. Thank you.